Right, thank you very much for the opportunity to talk. It's quite nice to be able to talk just after Ben, actually, who I temporarily lost. Because I guess it was the fact that he came out with his paper and also these other guys, Sang and co, that Avi was mentioning earlier, came out with their paper earlier in the year that kind of got me thinking about the idempotent theorem again. So I'm going to talk about as Gil said, quantitative aspects of the idempotent theorem. Right. Okay. So I perhaps should have said before. So the idempotent theorem is sort of the harmonic analyst's name for one of the things that Ben talked about earlier, and I'll make that connection. I was hoping to start by, if you like, explaining why we're interested in it from a mathematician's perspective. So I actually thought, in that regard, a little bit about some of the basic things I suppose that we do in the undergraduate syllabus at the university, and I wanted to start with projections. Projections are sort of, at least in this talk, I want to think about projections as ways of decomposing things like groups or vector spaces. So if G is, say, finite, abelian group, then we can write G is a direct sum of H direct sum K, or then we call a direct sum decomposition of G if H and K are subgroups of G, and H and set K is just 0. I was a bit worried actually with these boards that sort of stupidly when I saw Gil start that I was going to have to write right at the bottom. But of course, I'm just going to do what Gil did and start at my height and stop at my lower height. I don't know why it was concerning me earlier. Anyway.
Of course, there are clear notable differences.
Sure. Just a translation, there, isn't it? Slight dilation.
Parallel session.
And so, this relates to projections by defining a projection, let's say pi from G to G that takes.
Could you speak just a little bit louder, please, when you face the board?
Sure. So this relates to projections. In this way, we can define a projection associated with this direct sum decomposition. Just takes HK to H. Okay. And for any direct sum decomposition, you can define a projection like this, and it has the property that pi squared equals pi. And so if you have a homomorphism pi from G to itself, then you can also, that is a projection like this, then you can also define a direct sum decomposition. Okay. And why you care about direct sum decompositions to some extent because it's a way of breaking up your group G. Okay? And so you can also do this with, say, a normed space. So the projection on X is a morphism pi from X to X such that pi squared equals pi. Let's say finite dimensional. Not going to worry too much about analysis in this talk. Okay? But with normed spaces, we obviously also have a norm. And that norm, in some sense, gives you a notion of the quality of your projection. So it's natural, suppose this were, for a moment, infinite dimensional, it would be natural not just to ask for this to be a homomorphism of vector spaces, but it would also be natural to ask for it to be continuous. And then you could ask, that would be clearly the correct thing to do. And then you can ask, if you like, how continuous. And a measure of how continuous is the size of the norm. So the quality of this, in some rather nebulous sense, the quality of this direct sum decomposition is measured by the norm of pi. It's just the operator norm in this case. We may as well take it to be. Right, and so again, that's a measure of, if you like, how continuous this map pi is. Okay? So there's a few, maybe I can really labor this even a little bit more, and I could just consider a little example to emphasize what I mean. So if, say, x is r squared with the L infinity norm, they're just the max in the usual Cartesian coordinates, and E1 is just the vector 1, 1, and E2 is the vector 1, 1 plus epsilon for some tiny epsilon, then you could, and we'll define pi from x to x, just as an example of a projection. Just take say lambda 1 E1 plus lambda 2 E2 and map it to, well, just whatever, lambda 1 E1. Okay? So there's the E1 and E2 form a basis in the linear algebra sense of R squared. And so this is a sensible map, it's well defined, it's nice and linear. But it has a stupidly big norm, right? So linear map. It has a jolly big norm. Right? And that's because we chose an idiot basis, right? So if I want to make up, let's say, indeed, if I want to look at, say, pi of 0, 1, well, I guess I make 0, 1 in this basis by taking epsilon inverse copies of E2 minus E1. So that's the unique way of making it. Then pi of, excuse me, pi of 0, 1 is whatever, epsilon inverse E1. So norm of pi is at least somehow around epsilon inverse. So that's a bad projection, right? It's sort of it's a projection that just is reflecting this algebraic choice of what's going on. So of course, it's slightly, one thing that this highlights is the fact that projections and say closed subspaces, or just subspaces in the finite dimensional case, are not in some sense in one-to-one correspondence, right? You can pick there are a range of projections you could pick for a given subspace. Basically because if I give you a basis for a subspace, there's a range of ways of completing the superspace. So you could nevertheless pick a best projection pi, right? A projection pi with minimal norm, and that would be a sort of sensible thing to do. And if you do that, you can still show that as the dimension increases, you can construct subspaces in general, say if X is L1, where there's no highly continuous projection. And this just represents the fact that you can't, you can have subspaces where you can have finite spaces where the only complemented subspace is finite dimension, or co-finite dimensional, right? But I want to convince you in some sense that this norm somehow measures the quality of your projection. So it's there are sort of two things to come out of what I've said so far. So one is, right, it's a sensible thing if I give you a space to try and decompose it into smaller spaces. That's a sort of basic thing we do in maths. And the other is that in some sense we can measure the quality of this decomposition by the norm of the projection operator, to say the minimal norm of a projection operator corresponding to the decomposition. Okay? Those are the two things to remember from that. Maybe I should mention one other example. So, of course, if your Hilbert space, so I mean, R squared is a perfectly reasonable Hilbert space. We could have stuck L2 on here. This is still a basis, right? It's not an orthonormal basis. So if you're in Hilbert space, you can always pick your projections to be nice orthogonal projections if you just start with the subspace, in the obvious way. So Hilbert space projections behave particularly nicely, and the norm of a projection in Hilbert space is always going to be 1 for what we're considering. Okay? So the second thing to mention is that, one way of understanding, say, finite abelian groups G is through their representations. Okay, again, I suppose I claim if you're a mathematician you would like to understand groups, and you could do so through their representations. So let's say so. For example, we might be interested in some representation rho. So this is just a homomorphism from G into GL of X, where X is some finite dimensional normed space. So I'm using the norm here to stick a topology on. Hang on. Okay. So a very natural one. Maybe I can take it down here. So a natural example is if X is just L2 of G, and rho is the regular representation that takes F to the map, which maps F excuse me, it maps F to F of X minus Y. So this is the map rho Y it sends a function f in L2 of g just to the function translated around a little bit, right? So that's the usual thing, and that maps L2 to L2. And then it's well known, right, then that you sit down and you ask, ultimately you try to decompose this representation, this regular representation, into irreducible sub-representations. But we're just going to a first step. I mean, we all know what the answer is, so, or anyway, the answer is well known. But we're just imagining, just suppose you were just starting this game, so then you would start decomposing. Let's just call it row. So we might look for projection pi. Now, the projection would be on the underlying space X, right? So projection pi on from L2 of G to L2 of G. And then you want it to be compatible with the representation, right? So you would want to commute with the representation. Okay? So what I'm saying to you here is that this would be a natural a natural way of trying to split up this representation into two sub-representations. Okay? And if you did that, and doing this, you could, talk about the quality of this. As measured by pi. Also, in this case, because it's on Hilbert space, I told you earlier all the projections on Hilbert space you could pick. They don't all have norm 1, but you can, because in actual fact we're interested in decomposing L2 of G into two parts, not the specific. So we're interested in any projection that decomposes L2 into two parts, not the specific projection. You can always pick a projection that corresponds to that subspace decomposition, which has norm 1. So it's all nicely behaved. And so this is a little bit pointless. But I haven't just been wasting your time. So a natural alternative space you could consider. So this is less exciting. But so alternatively, we could consider row, again, algebraically the same representation, but this time into L1 of G. Okay? So algebraically it's doing exactly the same thing. It's translating functions around, but analytically it's going to be doing something slightly different because you have a different norm. Okay? So again, I just want to slightly rein everyone back in if some of this has been a bit vague. So rho here is just a regular representation. It's defined exactly like it is over there on functions. Okay? The only thing that's different from what we're doing over there is I've stuck a different norm on the space. Okay? It's the only thing. So this time I've got the L1 norm. Okay? So we could decompose it as we did up here, or we could try. Right? So then you have a slightly different situation. So This stuff, by the way, this is really just all. There's a book by Rudin, which more or less contains what I've been talking about so far. A Fourier analysis on groups. So Rudin, I guess, gets his knickers in a bit of a twist over some of the analysis, but since G is finite here, we're not. It's not a problem for us. But then we sort of. Well, what I want to say is I don't want to give the argument, but it's not a particularly difficult argument. So by sort of basic arguments, I know it sounds a bit lame. We get so firstly that because of this commuting with the regular representation, you get that pi of f actually has the form pi of f is f confolled with mu for some measure mu on G. So this just is some measure mu on G. I mean, G is finite, so it's, it's not particularly important. You could think of this as a function with it's signed, but a function where you could just take some of the kind of absolute values of the values of mu. Maybe since I haven't written down convolution yet, it would be helpful. So this is just that function. And then secondly, well, since I is a projection, we get that mu convolved with mu is mu. It's just that pi squared is pi. And thirdly, the operator norm of pi will not surprise you to learn. It's the norm of mu. Okay? And the idempotent theorem, as classically stated, concerns measures mu in the measure algebra M of G that are idempotent with bounded norm. Okay, and the reason that they were originally interested in these, or a reason they were originally interested in these things, is that once you understand, if you understand what they are, then you understand precisely how you could decompose, the ways in which you could decompose this representation, and in particular that the representation doesn't decompose in particularly exciting exciting fashion. Okay, so maybe I will, rather than state the classical idempotent theorem, so then I'll state the quantitative idempotent theorem. Am I managing to keep my voice up for you? Brilliant. So this was something with Ben that we worked on. It's already been stated, I guess, but so let's say, suppose oops, G to Z. Sorry, it's a bit of... Yeah, okay. So we've got a function, say, that's integer valued, or if you like, -1, 1. And I'll come back to why I've written the integers up there in a moment. But like Ben had -1, 1 here, and it's the same for what we're going to do. Where this norm is small, so this is the that quantity is small, then you can write f as a plus minus sum of indicator functions of cosets of subgroups of the group G, and there aren't that many. Okay, this is sort of dual to this. Okay, so G here is really G hat here. Okay, and that you can sort of make sense, right? We're looking at the L1 norm of the Fourier transform here, and we're really just looking at the L1 norm if I hadn't faffed with measures instead of functions. Okay. And then what I want to talk about today is really is getting rid of one of these exponentials. So as we heard from Ben, there have been many people earlier in the year have sort of strengthened different applications and aspects of this in different directions. So this is somehow still returning to the classical problem. It is just in terms of what you should expect to be true in this level of generality. If G is Z, for example, you can't get better than big O of M up here. You could broaden your idea of what a because your idea of what a subgroup is fixed, but you could be more inclusive about your notion of subgroup, and you could then hope to do better. But somehow, I don't know, I believe there probably is a fairly natural proof that will give a big O of M here. I don't know what it is, of course. But, somehow there is a natural theorem in there that is limited by obstacles that they don't exist over, say, groups, well, say over f2 to the n. If G is f2 to the n, those obstacles don't exist, but somehow they exist in Z, and so there's a class of proofs that would only that don't see the difference between different types of, say, finite abelian group, and I suspect within that class of proofs there's one that gives a big O of M here.
Sorry, can you repeat what do you believe the correct dependence is allowed on that?
Yeah. Basically because arithmetic progressions exist. Long arithmetic progressions exist. So groups where they don't exist, like f2 to the n, you hope to do better. Okay. I'm not going to, I sort of feel timing-wise it wouldn't be ideal. I'm not going to sort of labour the connection, but this, the reason mathematically you might care about this is because this characterises these measures mu in a not completely unnatural way, and therefore tells you how this representation decomposes. And I mean, yeah, that's a thing you could do. Good. Okay. So.
Sorry, John, this one. In your statement, G is.
G. Yeah. That's. Yeah. G is, for example, a finite abelian group. You can, barring this part, you can make it non-abelian, and you can also stick some topology on and spend some time mucking around with analysis.
So how does it look for ZP or something that has no subgroups?
Well, yeah. So that's good. Or Z if you're talking about finite sets. But yeah. So let's say Z mod PZ, it's P some large prime. So what this effectively tells you is that either F is, and so if you think of M as bounded, P tending to infinity but large prime, then it tells you that either F is almost always -1 or almost always 1. Right? Because there's only one, or whatever, there's only one big subgroup. So yeah, and that's, you see in that situation where the sort of, if I took an arithmetic progression of length p over 2, for example, then, so say, the indicator function of p a progression of length p over 2, then the that is log p in that situation, and that's why I expect big O of m here if you sort of go back, because somehow how many cosets of subgroups do I need? Well, you know, there are only two subgroups, the big one and the little one, and you know, you either use the big one or you don't, but it converts it into sort of the same thing, but then you have to get lots of copies of the little one.
Just to clarify, for small p, it could be much better. The L could be much smaller.
For small, yeah, so the size of the group you want to tend to infinity, but so yes, for example, z mod 2z to the n, thinking of p as in some sense being about the same as 2 to the n. Yes, yeah, so it could be, I think that's what Ben was saying as well, so anyway, that was, yeah, it could be that then, or at least, I mean, I don't know of any examples that, yeah, maybe it's that. Yeah, yes, so, but what I was trying to sort of say earlier, in, you know, rather feebly, was somehow, yes, I guess, so that would be nice, and that would be a really, you know, I suppose, potentially useful result, but, so I guess this with a big O of m, I guess there is some natural proof of that, and it probably works over the class of, let's say, finite appealing groups. And it would have some property where it doesn't really see the difference between, so we know sort of in practice there are lots of differences between this and this, but actually articulating exactly what they are in a way that's useful for proofs it's not easy for me anyway. Maybe other people do that better. But yes, expressing the fact that you have no long arithmetic progressions in this, for example.
If f is integer value instead of Boolean, then in the conclusion the sigma is also to be integer value instead of
no, because this is so rubbish. I'm not making them distinct, so I can just stack them up. So the L infinity of f is bounded by the, so this is a fact if I normalize it correctly. So that will tell you, normalize it so that that's true. And then, so I can just sort of cheat. But it's actually, it's good you raised that. It's excellent. Right. Okay. So with Ben Green, I think almost every instance of Ben so far has been Ben. Well, this is an instance of Ben Green. Okay. In this paper, we had the we had the following strategy. So let's say, suppose, just as an example, f is the indicator function of some set. Then we want to find some subgroup V and put and decompose f like this. So let me say what all these things are. So mu v, this is just the probability measure supported on v. So this is this obviously whoopsie daisy. This is obviously trivially true. And what we want is, so when you take the Fourier transform of these, the Fourier transform of this little guy is supported on the complement of v perp, okay, and the Fourier transform of this guy is supported on v perp. So the point is, it doesn't matter if you know what v perp is or not. All you need to know is that they have disjoint Fourier support, okay. And so what you have happen is the L1 norm of this must be the L1 norm of the Fourier transform of this guy on the left is equal to the sum of these two things. And so part of the plan will be, well, suppose we were really lucky, and also this guy here, so this guy is just the average value of A over cosets of V, that's what it evaluates to be. Suppose this guy were always either 0 or 1. Okay, it's quite unlikely, but suppose that we got that, okay? Then this guy would also be this guy would be the indicator function of a set, and this guy would be the indicator function of a set. And suppose those sets were non-empty, then by using the inequality Luca just mentioned, or this thing, then you'd have that each of these was sort of bigger than 0, so it would be at least 1. So you have a situation where the L1 norm of each of these parts is smaller than the L1 norm of the thing you started with. Okay, so you would, if all those things lined up in some lovely way, you would have found a nice way of decomposing your function. You could hope to run an inductive argument within this framework. Okay, super. So none of that works exactly, but all of it works roughly. So in particular, this guy's not going to take the values 0 or 1, but you can force him to take values very close to 0 or 1, and you can take the other arguments we want to talk about and make them kind of stable under some small L infinity perturbation. And yes, right, and you could, so you make this sort of, so we make a, so to make this work, we expand our class to consider what you could call epsilon almost integer valued functions. It just means that they are within epsilon being some integer value. So it's the usual thing of, if you have a bigger, it's easier to induct over a bigger class sometimes. Because although you've got more stuff you've got to throw, you've got a bigger target to hit. So sometimes that's a bonus and it's here. So the key problem, the reason that with Ben Green we ended up with doubly exponential bounds is when you do this expansion. So suppose now 1a was some is not 0, 1 valued, it's epsilon close to being 0, 1 valued. Then this guy here, this could actually be twice as bad, right? It could be somehow that this is within epsilon of being 0, 1 valued, and this is within epsilon of being 0, 1 valued, but somehow they're lined up in, for some points they're lined up in the wrong way. So somehow every time you would run this sort of inductive step, you'd split into things that were twice as bad in their almost integer valuedness as you started with, okay? So how bad would that get? Well, if everything I told you were to go through, you would expect to have to run this decomposition at least, say, m times or something like that. Okay? Because by that time you would then have got down to things which all had algebra norm. It's called the algebra norm. This L1 norm of the Fourier transform 1. So, I suppose by any stroke of good fortune, I started late.
You did?
Oh, brilliant. Do you know how late?
You have some.
We have flexibility.
Okay, right.
Also, if you need water, maybe this is water.
Yeah, no, yes, it is water. I hope it's water anyway. Yeah, so we'd be this whole scheme, in some sense, you'd expect to run about even times. So you're expecting your epsilon parameter to be sort of hit by roughly a 2 to the m. Okay, so that's something to sort of remember. So we will need as small as about 2 to the m. Okay, the point is it's exponential in m. Roughly, I don't know. Put a big O here. Okay. So I'm going to come back to that because this somehow is the hiccup, and there are 2 reasons that it's a hiccup, and they've both gone away. Okay. So now we need one trivial way of doing this decomposition would somehow be to pick V to be some space totally unrelated to A. And then this guy would sort of flatline a lot of the time. He'd be very small. Suppose A is really sparse, then he'd be really, really small. And this would sort of be, this would be epsilon almost integer valued, but actually the problem you'd have would be that this guy would also be very small, so your induction wouldn't work. So you genuinely need this to take kind of large values, okay? And so the first thing you do is you want to find some subgroup V that correlates with A. And that's something, there's a theorem for that, Feynman's theorem. So let me just, because I want to get to how we deal with this, so let me just, this bit will be a little bit quick. So it turns out by sort of some usual holder-jiggery pokery, this is true, where this is something called the additive energy. And then there's a theorem, Balog's theorem, really Gowers, Feynman, which says that if that's the case, then there's some subgroup in V of G such that this guy is large and hopefully I haven't. Occasionally it's possible to state this in a way that's obviously trivial. Yeah, I think that's good. Okay. I don't want to emphasize too much about this. Because of work of various people, things like Kreutz, Sask, and Thomas Schoen, this turns out to be a relatively good bound. What it's saying overall is somehow, if you have small algebra norm, so this part is easy, and this part, I guess, is hard. If you have small algebra norm, then you can find some subgroup, I'm going to say that, yep, subgroup V of G, such that A has large density on this subgroup, and the subgroup is not too small. Okay, and this turns out to be pretty big for that purpose. This was one of the, so this, when Ben and I wrote this paper, this was polynomial in M, and that was one of the ways in which we lost an extra exponential. Okay, I don't want to dwell on this too much, because this is not, that's just plugging in the fact that we have better bounds now.
So this is your result, the improvement of the
Yes.
Feynman-Gaussian.
Yeah, so right. Now, so now the other thing we want to do is, well, okay, let me give you a little bit of philosophy again. So this, this kind of bound, if the group G had some nice topology, this would tell you that f was uniformly continuous. It's just a uniform limit of continuous functions. It's continuous. Okay. And so somehow intuitively, incidentally, you see you have a continuous function taking discrete values. So you expect the level sets to be open and closed. In a topological group, the obvious things that are open and closed are open subgroups, because the complement of an open subgroup is a union of cosets of that subgroup, and a union of open sets. A coset of an open set is open, and a union of open sets is open. So all open subgroups are also closed. And you can obviously create open and closed sets by unioning and intersecting finitely open and closed sets. So you sort of intuitively expect the fact that this means continuous into discrete means level sets are open and closed. It turns out basically the only way to create open and closed sets in this context is from subgroups. That's sort of it's not a proof of anything. It's just kind of in your heart what's going on. So the idea then is, in some sense, 1A is bit continuous, and you can introduce a sort of quantitative continuity. So let me state a thing and then tell you what it means. So this is really the only new content. So suppose that f from G to C so again, we just got this nice one was M. P is some parameter for an LP norm bigger than or equal to 2, and epsilon is some sort of measure of how continuous this guy is. Well, I would like to do it relative to this subspace V, but I'm not going to bother for the minute. So then there exists V prime, a subgroup of G, such that so this tells you that the codimension of V prime is small. It's linear in P is the point, okay? And just polynomial in epsilon inverse at M. And this is some kind of notion of continuity. This tells you that F doesn't vary much from the average of F over cosets of V prime in LP norm. And the point, we were previously using P equals 2. The problem then is you need to make this epsilon needs to be exponentially small. Okay? If you're allowed to use P varying, then you can show that because this is the average value of this, that in actual fact this bootstraps epsilon at about 1 over M to being epsilon exponentially small in P. Okay, and so P is this linear parameter, just has to depend then only on M. Okay, so you can see, you get a linear dependence on P here by Chang's theorem or Rudin's inequality or Beckner's inequality or whatever you want to, there's a whole bunch of things that are the same thing, really. I'm almost finished. I'm sorry, because and so let me just show you the thing I said about being small. So this is somehow the way you save the other exponential by the fact that P depends, it's just large in M, not large in, it's just sort of linear in M, not exponential in M. So the point here is, suppose you know Suppose we just have a situation. Suppose A and G has density alpha, and you know that this is the case. So this is roughly, this specialized to F is the indicator function of a set, and restricted to one atom. Okay? Suppose you know that this is the case, and let's say alpha is less than a half. Okay, well then, measure of the set of X such that is large. Let's take and you have this, and so but this here just the measure of the set A, basically, if I've chosen my parameters sensibly. Alpha a bit smaller. So alpha, which is equal to the measure of the set A, is less than 4 epsilon to the p. So the point is, alpha being small gets bootstrapped like this to alpha being exponentially small. And making alpha exponentially small in p is less expensive. Okay? And you need to make alpha or epsilon, as it is over here, exponentially small because of this thing I mentioned before. Okay, so there are two places we lost before. One of them was in this part here, and the other one was in this part here. I know I've rushed that last bit, but hopefully you understood the first part, and maybe some people who are more familiar with it understood the last part. But I think I'll stop there. Thank you.
Questions, remarks? So this theorem is the new version, or this is the old version?
So this is the new here with just m.
So
four in fact, but
so e to the m to the 4.
4 plus little f.
And before it was doubly exponential. Yeah. And what
It's a different 4 from before actually as well.
And it's is this the truth already, or?
No, so probably. Well, I don't know that it's not the truth, but clearly it's not. I think it should be bigger of m.
M without the x at all? Or?
No. With the
the
x,
x.
sadly.
This is
Yeah.
more or less the
But maybe for what I was perhaps trying to suggest earlier is maybe if g is f2 to the n, for example, then this is.
I'm just visiting logician, so I'll ask a really dumb question. You outline very beautifully here mathematical structure, comparing several examples there. And earlier we heard many results there. But who would have guessed in advance that the study of the Fourier transform would give some information about complexity? I was really perplexed that there would be a connection there. I mean, I saw results, but who would have guessed in advance to do that?
The decomposing the regular representation over L2 is sort of exactly what the Fourier transform is. So you look for the Fourier transform is the unique, in some sense, change of basis that simultaneously diagonalizes all the operators induced by that representation. So in that sense, maybe I don't know whether that's something you also kind of come to after the fact, but you also, I suppose, at some stage had to have the insight that studying representations is a good thing, which obviously we kind of know it is now, but that was clearly, a good idea. Yeah, I don't know, so maybe that's a little, it's not a perfect answer. But.
If you take part 2 on the left independently, do you expect the correct dependency to be 1 over m? In the correlation, do you expect?
Yeah, in fact it is. I'm just, oh, 1 over, I was hedging because there's a 2 there, and yes, you're right, it's a, well, yeah, there's some question about the precise epsilons you have here. Sorry, just created epsilon out. You couldn't have made sense of that statement I just made. At least not the thing this should be like a 1 minus eta over m squared. And whether eta should or shouldn't be there, I don't know. Oh.
Essentially, this new proposition. So do you think that the parameters of the are tight, or the dimension?
So, I mean, with tight-ish. So, the M dependence. Maybe there'll be various questions about whether they happen together. But say the M dependence, I think, has to be at least linear for reasons of long arithmetic progressions. Epsilon to this has to be at least epsilon to the minus 2 for reasons of Nouveau sets. And this here has to be here sort of just for reasons of mass. You can't squeeze enough mass. Checking P is the easy one. But whether they all, maybe you could put a plus, it could be pluses and yeah, but it's not horrifically wrong. And the reason, I don't want to speak for Ben, but I guess the reason I was relatively convinced by the sort of doubly exponential boundary before was, well, yeah, one reason, but another reason here was somehow, well, we were using P equals 2, you sort of have to have this epsilon to the minus 2, so yeah, somehow, yeah. But it's a fair point.
So if there are no more questions, let's say stop again.